All right, welcome back. Today, we're not just going to talk about theory. Nope. We are actually going to step into the shoes of a nuclear engineer and solve a really critical problem. We're talking about how you stop a reactor core from melting down. So yeah, let's just jump right in.
So think about it like this. How do you safely control the temperature of a miniature star? Because really, that's what a reactor core is. It's this controlled chain reaction that's just pumping out an unbelievable amount of heat. And at the end of the day, the entire field of nuclear engineering really just boils down to one thing. How do you manage all that heat safely and, turn it into electricity? Okay, so to get a handle on this, let's zoom way in on the single most important part, the nuclear fuel rod. This is the heart of the whole operation. It's basically a long metal tube, and inside is where all the magic, or, the physics, happens. This is where fission creates that insane heat. If you get this component, you're well on your way to understanding the whole system.
All right, so let's get down to brass tacks. We are looking at a very specific engineering challenge here, the kind of thing an actual engineer would have to solve.
And this is it. We're not messing around with some simplified textbook example. No, this problem is taken directly from a prep book for a major engineering grad school test. It's designed to see if you really get the physics of heat transfer in probably the most extreme environment you could think of.
Okay, so let's unpack what they've given us. On one side, you've got all the stuff we already know. We've got the rod's diameter, the temperature of the water flowing past it, how much heat the rod is kicking out, and this thing called the heat transfer coefficient. That just sounds fancy, but it's really just a number that tells us how good the water is at grabbing heat and carrying it away. And on the other side, that's our mission. We have one single thing to find. What is the temperature on the outer surface of that rod?
So before we even think about punching numbers into a calculator, we need to pull out the right tool from our toolkit. And for this problem, the most important tool isn't a calculator at all. It's a really simple but super powerful idea from physics. And that core principle is called energy balance. You might hear engineers call it steady state, which basically just means things are stable. Think about it. If the reactor isn't getting hotter or colder, it means all the crazy heat being generated inside that fuel rod has to be perfectly balanced by the heat being carried away by the cooling water, right? It has to be. Heat in must equal heat out. It sounds so simple, but trust me, this little idea is the key to everything.
So you've really got these two forces at play. On the one hand, you've got the heat-in team. That's the volumetric heat generation, all the energy being created inside the rod. And on the other hand, you've got the heat-out team. That's the convective heat transfer. That's the water doing its job, pulling the energy away. And our whole game plan is to make those two things equal.
All right, time for the fun part, the calculation. Let's actually solve this thing step by step. And don't worry, it's not as scary as it looks. We're just going to walk through it, and you'll see exactly how that heat in equals heat out idea turns into a real answer.
Okay, so this is what that principle looks like as an equation. That stuff on the left, that's our heat in. And the stuff on the right, that's our heat out. See, we just set them equal to each other. And if you look closely, we know almost every number in here, except for one, T sub S. That's our target, the surface temperature. Now this is why you paid attention in algebra class. All we're going to do is shuffle this equation around a little bit to get our unknown T sub S all by itself on one side. And look at what we've got now. This is perfect. That first big chunk of the formula, that's going to tell us the difference in temperature between the rod and the water. Then all we have to do is add the water's temperature back in, and boom, we've got our final answer.
Whoa, hold on. Before we plug anything in, we have to do the one thing every engineer learns to do first. Get our numbers ready. You absolutely have to make sure all your units are speaking the same language. So we've got millimeters here, but we need meters. We've got kilowatts here, but the formula needs watts. So we just do a quick conversion, and now we're ready to go.
All right, let's focus on that first piece of the puzzle, the part that calculates the temperature difference. We plug in our heat generation, our diameter, we divide by 4 times our heat transfer coefficient, and what do we get? We get 625 K. Now, super important, this is not the final temperature. Remember? This is just how much hotter the rod's surface is compared to the water.
Okay, we've got all the pieces, we understand the physics, we've crunched the numbers, so let's get to the result and talk about why this answer actually matters in the real world.
So, let's put it all together. The water is 75 degrees Celsius. We just calculated that the surface of the rod is 625 degrees hotter than that. So, what's the final surface temperature?
It's just simple addition at this point. 750 plus 625 gives us our final answer, 700 degrees Celsius.
That is the temperature on the outside of that nuclear fuel rod.
But look, 700 degrees Celsius isn't just an answer to a test question, right? This number is critical. For material scientists, it dictates what kind of metal you can even use to build the rod so it doesn't melt. For safety engineers, this temperature is the basis for designing the entire cooling system, and for the people running the plant, it tells them exactly how hard they can push the reactor to make power while staying on the safe side of the line. It's a huge deal.
And that leaves us with one last, and maybe the most important question. The whole reason this works, the reason the temperature is a stable 700 degrees, is because of that perfect balance. Heat in equals heat out. This number shows just how incredibly vital that cooling water is. So, what happens if that cooling fails? What happens if the heat outside of our equation suddenly disappears? Where does that temperature go then? That is the exact question that defines the entire field of nuclear safety.